right? So the last class we saw that basically if you send in a reasonably strong optical wave, then due to electrosection in the medium, it can excite sound waves, right, which scatters your incident field, or specifically can backscatter your incident field into the Stokes field, right, slightly down shifted in frequency. And we saw that for reasonable powers like milliwatt powers and propagation lengths of like kilometer or something, right, in optical fibers, we saw that actually the gain that the Stokes experiences could be quite large, right? So basically as a function of propagation distance z, we send in some optical signal that we want, right, which acts as a pump. So due to Brillouin scattering, it decays as it propagates, right? So this is your pump, or basically the signal that you're sending, for example, for telecommunications, right? And basically from the other end, the Stokes wave starts acquiring gain, right? And basically a large fraction of your input power can just backscatter back into my transmitter because of this Brillouin scattering, right? So we saw that for milliwatt, like 10-20 milliwatts pump power for propagation distance of a kilometer or something, in a typical optical fiber, this gain that the Stokes experiences could be like 100 billion, right? So basically, you don't need any Stokes input from the other side. Any small fluctuation or noise, right, gets amplified so much that basically a lot or most of your pump input signal can be converted to the Stokes. Okay? So that at your receiver end, basically you receive very little or no signal, right? So this was a huge problem for optical fiber communications in the beginning, right? But turns out that as we've been going to higher and higher data rates, okay, that actually helps in reducing this backscattering, SBS backscattering, basically. Okay, so we'll see basically this analysis that we did was for monochromatic waves, right? So pump was at a particular frequency and then it scattered into Stokes at one particular frequency, downshifted by the Brillouin shift, right? But turns out that, so for optical communications, for example, right, you would send in bits. So there will be optical pulses of certain duration, right? And the higher the data rate, this duration of the pulses keeps going down, right? And we know that if you have pulses in the time domain, that means in the frequency domain you have a bandwidth, right? And the smaller this pulse width, the broader the frequency spectrum. And so if we'll see now that if the pump is actually not monochromatic, if it has a certain bandwidth, then we can actually reduce this backscattering, the efficiency of this backscattering. Okay. Okay, before that, basically in the initial days, one way where SBS was sort of awarded on its own was basically the initial days, the fiber manufacturing was not perfect, right? So basically there were inhomogeneities along the fiber length, right? So for example, the width of the core had sort of irregularities, right? There were bends in the fiber causing stresses, or the impurity concentration kept changing, and basically all of this. So we saw basically this Brillouin frequency shift, right, depended on material parameters like the electroreceptive constant, speed of sound, etc. Right. So basically all of these inhomogeneities cause a slight shift in omega, this Brillouin frequency. Okay. So basically what you can think of is basically instead of a single Brillouin frequency for the whole fiber, there was actually like a distribution of Brillouin frequencies at different lengths because just the fiber was not the same at different lengths, right? So instead of like, for example, you have pump scattering to Stokes with a single Brillouin shift. There is a broad range of frequencies due to this inhomogeneities, and you can basically sort of imagine that instead of all the scattering happening at one frequency, you sort of distribute it over many frequencies. So basically, this wave doesn't add up because at different stages you are adding different frequencies which are not coherent with each other. Okay. So basically, just inhomogeneities in the fiber sort of cause this SBS scattering to be inefficient. Okay, and that basically helped. Right, but then as the quality of the fibers kept increasing and they started becoming smoother and smoother and more homogeneous, then basically you start going towards this ideal case. Okay, so in that case, I mean, you can also think of this as what's happening is that, so remember we had a Brillouin line width, right? So there was some bandwidth over the gain which happened, which we referred to as the Brillouin line width gamma. So what these inhomogeneities are causing is like broadening in this line width, like some sort of inhomogeneous broadening, right? So if you know the concept of homogeneous and inhomogeneous broadening from maybe like other atomic physics or something, right? So basically what you're doing is adding different gain resonances here at different frequencies, artificially broadening the line width, and if you broaden the line width, the peak gain goes down. Right? So basically you can think of it like that. So fiber inhomogeneity is helped, but as the fibers became better and better, then the Brillouin scattering also got worse. Right? So then to avoid that, basically what people do is, as I said, go to this fact that basically if the pump has, instead of a CW wave, if it has some bandwidth, right? Because here you see that this Brillouin has a gain bandwidth which is quite narrow. Okay, so if you make the pump bandwidth bigger than the Brillouin gain bandwidth, right? It's sort of going to this case here, right? Instead of sort of broadening the gain line width, what you're doing is your input itself is very broad, much broader than the, let's say, the Brillouin line width, which lowers the Brillouin gain, effective Brillouin gain. Okay, so let's quickly see that how that can happen. Right, so basically these pulses have some duration, right? Which, for example, depends on my data rate, right? So if the pulses have a duration which is smaller than the inverse of the Brillouin line width, or this was, as you remember, the phonon lifetime, right? So if your pulse width here is much smaller than the phonon lifetime, then basically we'll see that the effective Brillouin gain goes down. Okay, so it's sort of you're not allowing the acoustic waves to build up. Right? Before that, my optical pulse has disappeared already before the phonon sort of builds out, right? Equivalently, you can see that my spectral width needs to be greater than the Brillouin line. Okay, so if the spectrum of my input beam here is broader than the Brillouin line width, then basically you'll see that you can reduce this SBS gain. Okay, so you can reduce this backscattering. Okay, So let's consider a case where, so for example, I have a pump which has a finite spectral width. Okay, so it has a center frequency omega p naught. Okay, and then it has a spectral width delta omega p. Okay, so so this could be, for example, if you have pulses here, then it could just be so delta omega p will be 1 over tau p, right? Or you could also broaden the spectrum here using other modulation techniques, right? So this is just simple sort of on-off keying. You could have phase modulation or other kinds of modulation, but basically anything that you do so that the spectrum is now has some bandwidth. Okay. So now we can look at the frequency downshifted from omega p naught by this Brillouin frequency omega b. Okay, so that Stokes frequency is omega s naught. Okay, and then we want to see basically what is the gain that this Stokes frequency at omega s naught experiences. Okay, so if this was just a monochromatic pump beam here, if delta omega p was 0 basically, then we saw that there was a Brillouin gain here, whose peak was at omega b, right? And so then this will get amplified with the peak gain. But now you can see that there's a range of frequencies, right? So each frequency will contribute sort of its own Brillouin gain, but they'll all be shifted from each other. Right. So, for example, let's look at a frequency here, omega p, a particular frequency here, omega p. So, what will this do? Right. So, this will cause its Brillouin scattering at so omega b down from this pump frequency, right? So for this particular Stokes frequency that we are looking at, omega s naught, you can see that it's away from the peak for this pump frequency. Okay. So if we call this distance omega, yeah.
So for a single pump frequency, there will be a band of Stokes frequencies. For a single pump frequency, there will be a bandwidth of Stokes frequencies.
For a single pump frequency, we saw that the SBS gain has a line, right? So the peak gain occurs at omega b, right? But nearby frequencies within a bandwidth gamma b can also experience gain.
And so when they add incoherently, so as a result, the bandwidth will more increase or decrease?
No. So in this case, when the pump is monochromatic, right? So imagine here you have some noise present at different frequencies, right? Basically, the one which builds up the most will be the one at the center of the gain, okay? Because it has maximum gain, right? So and basically we saw that this comes in the exponential, right? So this is some line shape g of omega, and we saw that this comes in the exponential, right? So the center frequency will be the one which is exactly omega b downshifted from the pump, will be the Stokes frequency which builds up here. Okay. Other frequencies have lower gain and they sort of don't build up. So it's like for example, in a laser, right? You have different modes, and the mode with lasers which builds up in power is the one which is closest to the gain peak, right? Other modes could also acquire gain, but the one which is closest takes over because it acquires the maximum gain. So it's similar here. Okay. But of course, if you send in some wave here which is slightly away from the center frequency, then it will acquire gain which is of a slightly lower value. Okay. But now what we want to do is basically reduce this peak gain. Okay, because this backscattering can cause all my signal to come back, right? So basically, I want to reduce this peak gain. So I want to make this look like something like this, right? So if I'm looking at a particular frequency, so here I'm looking at omega s naught, right? So omega p naught is my pump center frequency, and if it was monochromatic, then the frequency which will build up is omega s naught, which is exactly downshifted omega b, right? But now instead of monochromatic, I have a slightly I have a finite bandwidth, and then I want to see how this omega s naught builds up, right? If the gain that this sees now is lower, then that helps. That's what I want, right? So is that clear? What we are trying to do?
Yes, sir.
Okay, so basically what we want to see is how much gain this frequency experiences as a function of this delta omega. Okay, and basically what we'll see is the gain goes down as this delta omega p increases. So the maximum gain happens when, of course, very small or 0, right? And as we keep increasing, the gain that this sees keeps going down. So basically this backscattering will keep reducing. Okay, which means more of the signal gets through. Okay, so yeah, so now basically we want to see what is the effective gain that this frequency experiences. Okay, so basically what we need to do is pick a frequency here within the bandwidth, right, and see how much gain this experiences because of this frequency, and then just change this frequency across the bandwidth and integrate. Right? So the effective gain seen at omega s naught, right, which is so omega s naught is the pump center frequency minus the Brillouin shift. Right, so we can find it out by integrating over the pump bandwidth, the Brillouin gain, right? So let's say this pump profile is given by some function s of omega p, right? So for example, it could be a Gaussian function, right? Or it could be Lorentzian or whatever, right? So that's the line shape of my input spectrum, right? So due to a frequency omega p, which is at a distance omega from this omega s naught, right? So this omega p gives rise to this Brillouin gain shape, line shape, right? So you can see that this omega s naught is now away from the gain peak due to this frequency by omega b minus omega, right? So that's sort of the detuning for the gain peak for this particular. So if I change the frequency, this will shift, right? And this will now be detuned by a different amount, right? So basically we are adding all those effects, right? So for this frequency omega p, the gain would be, so remember we had a Lorentzian line shape for this gain. Right, so this omega b by 2 so omega b is the line width here. Sorry, gamma b is the line width here, right? And then here comes the detuning part. So that's omega b minus omega. Right? Times so I weight it with the pump amplitude at that frequency and then integrate over the pump frequency. Okay, so that would be the effective gain. Is that clear? So for example, for a monochromatic pump wave, this S of omega p will be a delta function, right? And in that case, if it's a delta function, you can see that you'll just recover the gain at center, right? So if it's a delta function, then omega is equal to omega p, right? And you'll just pick out the gain center here. So it will just be GB, the maximum gain. Okay, so with the, as I said, so we can assume some function for this spectrum. The most common thing to assume is a Gaussian function because that sort of I mean, a Gaussian function approximates many things well. So you can assume a Gaussian shape for this. You can assume a Gaussian shape, right, for this spectrum. So center is at omega p naught with the width omega p, delta omega p. Okay, so for example, if these are Gaussian pulses in time, then we know that the Fourier transform is also Gaussian. Right? So, for example, that would be one case. Right, so basically we plug this Gaussian form here. Right, so the spectrum is normalized such that this is one. Right? So this is giving you the fraction of the pump power at that particular frequency. Okay, so one thing, so basically we need to sort of solve this integral. One thing to see is that, so this factor omega b minus omega, which is this quantity here, you can see that's the same as this quantity here, right? Basically, how much the pump is shifted from the center frequency is how much this is detuned from the peak, right? So this I can also just write as omega p minus omega p naught. Right, because I want to convert the integral in terms of omega p, because I am integrating over omega p. So, right, so this quantity is the same as this quantity. Okay, so the integral that you end up with is okay. So that's the integral. So now the only variable is omega p, and so we'll get an answer in terms of this GB, gamma p, and delta omega p. Okay, so to evaluate this integral, so we can do a change of variables. We can define this quantity omega p minus omega p naught as x. Okay, so this integral just reduces to okay. So it's like an integral of a Gaussian function multiplied by a Lorentzian function. Okay, so this integral is actually well known. So there is an identity Okay, so this integral, the answer is in terms of the error function. You know what, right? The error function is basically, or this is the complementary error function, which is, if you recall, is the integral of a Gaussian function. Okay, so the error function of complementary error function of x is the integral from x to infinity of a Gaussian function. Okay, so if you use this identity here, then you see that the effective gain Okay, so now you can see that we are getting the answer in terms of this ratio of gamma b by delta omega p. Right, so the gamma b is the Brillouin gain line width, and delta omega p is the width of our input spectrum. Right, so it comes in the error function and this exponential here also. So basically, this error function is the one which is reducing the gain. So as this ratio gamma b by delta omega p decreases, which means our input spectrum is wider than the Brillouin gain line width, then this factor is smaller and smaller, and the effective gain goes down. Okay, so we can define this ratio So let's define this Q as this ratio of so gamma B over 2 or delta omega B. So the ratio of the Brillouin line width to the pump spectrum width. Right. So in terms of this Q parameter, I can write my effective gain as right. So it goes as some Q times e to the Q square times the error function of Q. Okay. So we want smaller Q, right? So as Q goes down, each of these factors go down, right? And so my effective gain decreases. Okay. So basically, to reduce SBS backscattering, we want this Q to be less than 1, right? Equally, this delta omega P should be bigger than gamma B. Right? So for small q, for q much less than 1, we can take limits for these functions. Okay, so e to the q square we can approximate as the Taylor function, keeping only the first term, 1 plus q square. Okay, and the error function of q is just then the error function of 0, which is we can approximate by error function of 0, which is half. Okay, so when q is much smaller than 1, then this ratio of the effective gain to the actual peak Brillouin gain right like this. And again, if q is much smaller than 1, then q is actually much bigger than q squared, so we can neglect even the q square here. So this goes as some square root of pi by 2 times q. Okay, and the square root of pi by 2 is also, it's close to 1, so you can sort of approximate it goes down by a factor of q. Okay, so how much the gain goes down is by a factor of q, which is the ratio of the Brillouin line width to my pump spectrum. Okay, so for example, if my pump spectrum is twice the Brillouin line width, right? So if q is half, then this gain goes down by half, right? And as you keep roughly, and then if it's 1 by 10, then it goes by 1 by 10. So remember this gamma b was, or gamma b by 2 then was roughly in the range of, let's say, 5 to 50 megahertz. So for silica optical fibers, right? So for example, if I choose delta omega p to be 500 megahertz, so it doesn't need to be very broad, right? 500 megahertz is actually quite narrow by optical standards, right? So then, so this ratio is for 50 megahertz, this 1 by 10, so you can reduce the effective gain by 1 by 10, right? So instead of, so here exponential gain of, so we saw that you could get like e to the 20 or something, you reduce this by factor of 10, you go down to e to the 2, so which is only like a factor of 10 or something. So right, so then if you have some noise here, it only amplifies by a very small amount. So you don't backscatter your pump into the stokes much at all. Okay. So already, so for example, if you have 1 nanosecond pulses, roughly, so let's say you have 1 gigahertz data rate, then already that means you have roughly like 500 megahertz or 1 gigahertz bandwidth. So that already tells you. Modern day data rates are like tens of hundreds of gigabits per second, right? So these pulses are tens of picoseconds to maybe 100 picosecond, right? So then Q is like 1 over 100 or something. So now this is not an issue. Brilliant scattering is not an issue at all. Okay. Another way is if you want to send in actually, if you don't want to send in pulses here, if you have some other kind of scheme, or if you want to have constant intensity, then you can also do phase modulation. Okay, so instead of this intensity modulation, one can also do phase modulation. So let's say, for example, you want a strong pump wave propagating a fiber to do some other kind of nonlinear process, right? So you want to eliminate Brillouin, but have some other kind of nonlinear process. But you want sort of a quasi, or you want a CW, a constant intensity pump. So then what you can do is you can do phase modulation, right? So basically, I have some pump frequency e to the I again. So this, let's say P naught, right? So e to the I P naught T is my usual monochromatic pump, and then I apply some phase modulation on it. So phase as a function of time. Okay. So this, for example, you have electro-optic modulators available, right? So standard ones which can go up to speeds of tens of gigahertz, right? So they are based on electro-optic materials like lithium niobate. So you can use these phase modulators and apply some phase onto your pump, right? So for example, typically you can just use a sinusoidal signal and apply sinusoidal phase. Some sine omega mt, right? And you just choose this omega m to be greater than your Brillouin alignment, right? So again, this is roughly 10 megahertz. So if you choose 100 megahertz, 1 gigahertz, I mean, you have modulators available which go up to even 50 gigahertz, right? Then you can basically, so this phase modulation results in a broadening of the frequency spectrum. Right? So for example, what we saw when we were discussing dispersion, that a time-dependent phase gives rise to a frequency shift, right? d phi by dt will give me a frequency spread, and that spread is given by how much is omega. Okay, so you can easily do this. You can do phase modulation at 100 megahertz or 1 gigahertz, 10 gigahertz much easily. So you can basically make this Q very small, 0.1 or 0.01. So basically suppressing the effective Brillouin. Okay, so I hope that is clear how to reduce this Brillouin backscattering mainly for optical communication purposes. Okay, because this was actually a very big issue that all my signal just comes back. Right, so for optical communication, I guess SBS is sort of a problem that you want to eliminate. But of course, Brillouin scattering has its own applications. We'll look at some of them. So mainly, so for example, where you want or where Brillouin scattering becomes useful is for actually RF or microwave electronics, right? So this Brillouin frequency shift we saw was, so for silica it's 11 gigahertz, and then like you can dope the silica by different amounts and atoms, and you can sort of shift this around a little bit. So let's say from 8 gigahertz to 12 gigahertz. And then if you use different materials, then you can also have them go up to 20, 30 gigahertz. So in the gigahertz range, it's sort of the frequency range for radio frequency and microwave electronics, right? So traditionally, if you try to use electronic equipment at these frequencies, they are actually quite expensive, and some of it's difficult to get, for example, low noise equipment at these working at these frequencies. So SBS is actually used. So photonics using SBS is actually used as a sort of medium to manipulate or generate microwave or RF signals. Okay. So, for example, if you beat the pump and Stokes together onto a photodiode, then the photodiode will give you a beat signal, which is the difference of the frequencies of the pump and Stokes, right? So in this case, it will just be the Brillouin frequency, right? So that it will give you a current which is varying at that frequency. So it's like an electronic source at microwave source at whatever 11 gigahertz, right? And it can be actually very low noise because the Stokes is generated from the pump, right? So and we have very low noise lasers which we can use as pumps. So you can get very good sort of microwave sources like this. Okay, so one thing that we need to consider is actually gain saturation. So we saw that we can actually get very large gain, right? Where basically we start converting a lot of the pump, like 50%, into the Stokes. So then we need to start considering the depletion of the pump. Right? We can't. So this exponential gain was in the pump undepleted limit. Right? But once you start converting a lot, like more than 10%, then you need to start worrying about pump depletion, right? Or equally, what that means is gain saturation. The gain won't keep increasing exponentially. Once the pump starts depleting, then it will sort of start saturating. Right? So let's consider some waveguide, right? So you have pump propagating in the plus Z, like that. Then the Stokes coming in the backward direction, like that. Okay, so let's consider a length L. And so we know the propagation equations for the intensities of the pump and Stokes. You remember we had like this. Right, so Stokes is traveling in the backward negative Z direction, and it acquires gain. The pump is traveling the forward Z direction, it requires loss. Right, so we saw this last time itself. Of course, if you just add these two equations, you can see that IP minus IS is a constant. Right, so let's denote this constant by some capital C. right? So anywhere at any distance, the difference in the pump and Stokes intensity is a constant, right? So we saw that the pump goes down, the Stokes comes up, but the difference remains the same. Right, so in the Stokes equation, for the pump intensity IP, I can substitute C plus IS. Okay, so right. That, right? So the pump undepleted case will be when we neglect this, right? We say, okay, IP is sort of constant, and then we just use a constant IP here, we get exponential gain. But now here we are considering the pump depletion also, right? So we get this equation for the Stokes. So you can gather the terms for the Stokes on one side. Okay, so we take the Z on the other side, integrate from 0 to Z. So you just get Z, GB times Z there. And we take IS times IS plus C here. So here we get 1 over IS times IS plus C, which I can write as 1 over C times 1 over IS minus 1 over IS plus C. Okay, so now these are simple integrals, right? Dx over x. So we know the solution is a log function. So okay, so get that. And now, so log of A minus log of B is log of A by B, right? So divide this by this. And then we can take the exponent on both sides, so we get okay. And so now I can solve for IS of Z. Okay, so I can take this term on to this side, and then I get a linear equation basically for IS of Z, right? So you can see that I can write IS of Z as Okay. So we've solved for IS at Z in terms of this parameter C and IS of 0. Now IS at 0, actually we don't know a priori, right? That's basically how much Stokes ends up after amplification at my input. What we know is IP of 0, right? That's the pump that we send in. Right, so we can convert the IS zeros into IP zeros by this relation, because at Z equal to 0 also this relation holds. So IP 0 minus IS 0 is C. So we can substitute that there. Okay, so first thing we can just do is put C equal to IP 0 minus IS 0 here. Okay, so this. Okay, so then we get I set Z is okay, so we get that. Okay, so now we can define SBS reflectivity, which is basically IS 0 divided by IP 0, right? So how much Stokes I get back divided by how much pump I'm sending in. So RSBS is the SBS reflectivity. So the fraction of power which comes back as Stokes. So then in terms of this reflectivity, you can write IS of Z as okay. So the Stokes intensity at a distance Z is given a function of this R SBS reflectivity times my input pump, and this G of Z here is given by e to the 1 minus G naught Z, where G naught is GB times IP naught. Right, so we have factor of GB times IP naught here. We say that is G naught, which is basically the unsaturated it's also called the unsaturated small signal gain.
So the rightmost part of the blackboard is not visible to us.
Okay. Is this part visible up to here?
Yeah, yes, sir.
GB IP naught? Okay. Yeah. So this, now I can get this. right? So this G naught is called the unsaturated small signal gain. Right. So when basically the reflectivity is very small, which means the pump is sort of undepleted, right? So if when R SBS is much less than 1, which means IS of 0 is much smaller than IP0. So the conversion is very small, then basically you can see that the gain will just be given by e to the I G naught Z. So that's why it's called the unsaturated gain. Okay, so from this expression for Is of Z, we can put Z equal to L because that's the input Stokes power, right? This is the input Stokes from the other end. So we define this F in the input Stokes intensity divided by the input pump intensity, right? So Stokes is input at L and pump is input at 0. So this we know, right? Because this is our input parameters. So let's say we are using this as an amplifier, right? We are sending a strong pump, a weak Stokes. So we know how much we are sending in. So we can put IS of L from here, right? So we just get G of L here, which is this e to the I 1 minus R times E naught L. Okay, so I can also write this as putting the expression for the G of L. Okay, so I know this Fn, and the unknown on the right hand side is this RSBS, right? The SBS reflectivity. So this is a transcendental equation. Right, so all parameters. So I know Fn, I know G naught, because that's just the Brillouin gain factor, which is the material property times input pump intensity. L, of course, I know the length. So the only unknown is RSBS, right? So, but this is of course I mean, ideally, what I want is RSBS equal to something, but this is a transcendental equation, and we cannot get it in that form, right? So basically, it's a transcendental equation that you have to solve for RSBS. Okay. Or from here, once you know RSBS, then you can know the Stokes power at any point along the way, right? right? And typically these transcendental equations you solve using graphical methods, right? So, for example, you plot the left-hand side and the right-hand side as a function of your unknown quantity R, and then see where they both intersect. That intersection point gives you the solution. So typically, how the curves look for IP and IZ, right? So IP goes down with increasing Z, so and IS builds up with decreasing Z. So right, so basically for different F in, for different input conditions, I can calculate what the RSBS is, and then from there I can calculate what the source power is at each distance, and from that I can calculate what the pump power is also at each distance, right? So, for example, typical curves you get like this. So IP going down, IS is going up, right? So this is, for example, for the solid line is for F in equal to 10 to the minus 3, right? Which means my input Stokes from the other side is 1,000th of my input pump. So we get curves like this. So here it starts from basically 10 to the minus 3, right? And you can see that almost 50% of my input pump gets converted to, right? So for this graph, the gain value here is, so the G naught L is taken to be 10. Right, so the unsaturated gain would be e to the 10. So in the pump undepleted limit, the gain should actually be e to the 10. But you can see that as the slopes increases, now the pump is starting to get depleted. Right, so the actual gain here you get is not e to the 10, but whatever, like 0.5 divided by 10 to the minus 3. So if I plot this for a slightly different Fin, so if I plot the dotted line for, if I increase the Stokes power by a factor of 10, so Fin now is 10 to the minus 2, then the pump gets depleted more because I have more Stokes here, right? So the Stokes actually goes up to about 70%. Okay. So yeah, so you can see that when I increase my input Stokes by a factor of 10, my output Stokes of course doesn't go up by a factor of 10 because it can't. It was already at 50% conversion, it only goes up to like 70%. That's because of gain saturation. Okay, another way to plot this is so if I plot the reflectivity, SBS reflectivity as a function of this unsaturated gain G naught L, right, which is GBI input pump intensity times L. So sort of x-axis you can think of as input pump power, and y-axis the SBS reflectivity. So of course the maximum reflectivity can only be 1, right? That's 100% of my pump comes back. So of course as I increase the pump intensity, the reflectivity increases. So goes like this, and eventually it saturates because it can't exceed 1. Once you start getting close to 100% conversion, it saturates. Sorry, is there a question?
Sir, board is not visible to us.
Oh, the whole video went away?
Yes, sir.
Is it back?
Yes, sir.
Okay. So as I increase pump power, the reflectivity increases, right? And I can plot this for different values of my input Stokes power, for example. So you get different curves for different input values. Okay, and so this is sort of so this is f in 10 to the minus 2, this is 10 to the minus 4, 10 to the minus 8, 10 to the minus 12. Right, so as you increase input Stokes power, you get higher reflectivity, of course, because you're starting with more Stokes power. But eventually everything saturates, right, as you keep increasing pump power. So some scales on the x-axis, so this is 0. Okay, so you can see that once you start exceeding, let's say G0 L equal to 50, then even for a very small input, 10 to the minus 12, right, which you can consider basically just as noise. So no input here, just background fluctuations or vacuum fluctuations, some noise at the Stokes, right? That gets amplified such that, for example, you can get more than 50% reflectivity. Okay, so in this regime, this SBS amplifier is called sometimes as SBS generator. Right, basically, which means you just need no input Stokes needed. So you just need a input pump, and then from noise itself, Stokes gets amplified a lot, right? So, for example, you can generate a microwave signal by beating the pump and Stokes, but you don't need to have a Stokes. You can just start with a pump, right? And if you have enough pump power, then the gain becomes so large that the Stokes gets generated on its own, and then you beat these two on a photodiode and you get your microwave signal. Okay, so those are called SBS generators. One last way we can sort of plot this effect is you can also look at the effective gain that the Stokes experiences. Right, so we can define as actual gain or saturated gain. GS, which is basically Stokes output divided by Stokes input, right? That's the actual gain. we can define an unsaturated gain, which happens in the limit of undepleted pump. That will just be e to this exponential gain, I P L, right? So for small gain values, or when the pump depletion, the conversion from pump to Stokes is small, then you get this gain approaches this. But as the conversion becomes more and more, you start deviating from this unsaturated gain, right? The actual gain goes down because so you can see this sort of starts saturating, right? So if you plot GS divided by GA, again on the x-axis as a function of Fin, so GA times Fin to normalize sort of, right? So this is proportional to input Stokes power. Then you see for small values, of input, the actual gain GS is equal to GA, but as you increase the input, the gain goes down. Okay, so this is basically gain saturation. As I'm increasing my input power, gain actually goes down because of pump depletion. Okay, so again you can plot this for different. So this is for an unsaturated gain of 10. This is for 100. Okay, so the higher the unsaturated gain, the faster it starts falling because you reach pump depletion faster. Right? So at a smaller input itself, the gain starts falling. Okay, so basically in Brillouin, it's very easy to see these big pump depletion and gain saturation effects. So that's why it's important to consider them. Typically, like in amplifiers, usually you don't reach the pump depletion limit. But in this case, yeah.
Sir, we reach pump depletion in saturated gain.
Yeah, saturated gain happens. So why is this leveling off? Because the gain gets saturated.
Saturated.
Right? So in this case, as I'm increasing my input, so because my input pump power is fixed, as I increase my input Stokes, for the same gain, the output Stokes keeps increasing, but at some point it becomes comparable to my input pump, right? So now if I keep increasing my input Stokes, the output Stokes can't keep increasing by the same factor. So the gain has to go down because my output is clamped by the input pump, right? So that's why on the x-axis I'm increasing input Stokes power. If this was flat, then output Stokes power is scaling with my input Stokes power, constant gain, right? But I cannot have constant gain because for a constant input pump power, once my output Stokes power starts becoming comparable to my input pump power, then of course the gain has to reduce because I can't exceed my input, right? That's the pump depletion. That's right.
Okay, sir.
Right. So again, in this case, for example, when I'm increasing here by 10 times, the output here doesn't increase by 10 times because it can't, right? You are sort of you can't convert more than all of your pump. So here you go up by 10 times, but here you only go up by a factor of 1.5, and that's because of the gain going down. Okay, so those are the effects that you need to consider when you use like SBS as an amplifier, right? For example, to generate microwave signals, etc. Now again, like for this SBS generator case where you don't need any Stokes and you generate Stokes spontaneously, or like the non-spontaneous noise amplifies so much that you get a right Stokes, you can also, just like the Raman case, right, or any other like we saw for the parametric amplifier case, once you have some mechanism of amplification, again you can put this amplifier inside an optical cavity, and then if your gain exceeds the loss, you can make a laser, right? Similarly, you can make Brillouin lasers. Just like, for example, Raman lasers we saw, you also have Brillouin lasers where now you do this SBS inside an optical cavity. Right, and it's exactly the same. I mean, what we discussed for Raman is exactly the same effect happening here, except, yeah, just the frequencies involved are a bit different. Right, so again, what are the applications of Brillouin lasers are again low noise microwave sources. So let's say you want to generate something at 11 gigahertz, an electronic signal with very low noise. To do it with pure electronics is sort of difficult with very low noise, especially once you start going to higher frequencies. But using this SBS, so what you can do is just start from a pump laser, and laser you can get very, very low noise lasers. Especially single frequency lasers are very low noise. So the basic idea is to start with a pump laser. Right? You sort of split up part of it and send part of it into a ring cavity. Right? And then inside the ring cavity, you have SBS going on. So this could just be a fiber wound up, right? Or could be any kind of optical resonator. And so you're generating Stokes. And if the round trip gain exceeds the round trip loss, then you get lazy, right? And then Stokes comes out here. If you exceed sort of the threshold, right? Gain loss. And then what you can do is sort of send your pump and Stokes onto a photodiode, and then this photodiode will see the bit frequency between the pump and Stokes and give out a microwave signal whose frequency is basically the Brillouin frequency or the difference in the pump and Stokes, right? And if you start with a very nice single frequency, very low noise laser, then here this can be a very pure tone with extremely low noise. Okay. Right. So, and the analysis is exactly the same for Raman lasers, right? Because we saw that the equation was also the same, except just instead of Raman gain, you have Brillouin gain. So the threshold power for this lasing, so the formula is basically the same that we got for Raman lasing, except you have Brillouin gain instead of Raman gain. Right, so there we saw, for example, the threshold power scale with the mode volume of this optical cavity and inversely proportional to the Q factors at the pump and Stokes. So for Brillouin scattering, basically the pump and Stokes are very close, right? So this is only say 10 gigahertz. Then basically we can just replace lambda p and lambda s by the same and QPS QS by the same. So So it scales at mode volume divided by square of the quality factor, and of course it scales as 1 over the Brillouin gain. Okay, so basically what is happening, if I look at the output Stokes power here as a function of the input pump power, then basically until I reach threshold there is nothing. Once I cross threshold, then I get Stokes power. Okay. And again, so this cavity will have resonances, and then you want to match. So you pump at one of the resonances, and then you want to match the Stokes resonance to lie within the gain bandwidth of the Brillouin gain, right? So, like recall, for example, for the Raman case, we had the same issue, and then one way to do it was if I make the cavity big enough such that the FSR, so this is Brillouin line width, this is cavity FSR, right? So if I make the FSR smaller than the Brillouin line width, then I ensure that my Stokes mode is within the range. So this you can do for fiber cavities, because recall that this gamma b is very small, right? So for Raman we had this line width to be hundreds of gigahertz or terahertz, but here it's like 10 to 100 megahertz. So, and this FSR, recall, scales as 1 over the length. So we need really long length to ensure that the FSR is small enough to lie within them. Right? So this you can do with fiber-based cavities where you can make this many meters long. So, and that's how basically fiber Brillouin lasers are made. One another application for fiber-based Brillouin lasers is actually for gyroscopes. So gyroscopes are devices basically which detect motion, right? Like rotation, to sense sort of orientation. So like for example in aircraft, etc., you want to know where you're going, right? So you need gyroscopes to know exactly which direction you're pointing and if you're rotating, by how much you're rotating, etc. So there are different kinds of gyroscopes, like mechanical gyroscopes, etc. Right? But with these kinds of optical gyroscope, you can actually get very good performance. So basically, what happens is, so imagine you have this cavity, right? And now this is placed on some platform which is moving. So now, if that platform is rotating, okay. So recall here that the pump and Stokes are counterpropagating, right? Because SBS we saw was mainly, especially in fibers, they go backward. So if this thing is rotating in one direction due to the Doppler shift, the pump will be shifted in one direction and the Stokes will be shifted in the opposite direction, right? Because they're opposite sense with respect to the rotation. So with respect to this external rotation, so if this external rotation is happening at some frequency omega, then this beat frequency, or let me call it, I don't know, omega rotation, then this pump will be upshifted by omega. Or in this case, the Stokes is in the, a pump will be upshifted and the Stokes will be downshifted. So this beat frequency that you will get will be shifted by twice of this rotational frequency. So you can sense if whatever device you are on is rotating at some rate or not. Okay. And with these fiber-based gyroscopes, you can really sense very sensitive motions.
So in this diagram, So the pump is going in the forward direction, so the stroke should be going in the opposite direction. So that should be going on the opposite direction to that of the pump in the fiber.
Yeah. So I guess I drew this wrong. So if the pump is going like this, then yeah. So the pump is going like this, then the Stokes comes back. Right. So pump, and the Stokes actually comes back. You're right.
And sir, the rotation is in 2 dimension or 3 dimension for the optical gyroscopes.
So this is
Because
a 2D device. This is a 2D. I mean, because it's a cavity. It's like it's sitting on a 2D plane, right? So it will sense the motion in that plane. So if you want to have 3D device, then you need like one gyroscope like this and then one on the perpendicular plane. If you want to sense total 3D motion. So, right. So this one will detect in the plane what is the motion.
And sir, how does the frequency of the strokes and pump change on rotation?
So that's the Doppler effect, right? So, right. So what is happening? So the wave is traveling through this medium, and this medium is moving.
Okay, sir, I got.
So it's the Doppler shift. Right. So yeah. So I mean, you can do this in fibers, but people have recently started doing these things in on-chip microcavities also, so on a much smaller scale. So for that, of course, my length of the cavity now is very small. So V effective goes down a lot. So my threshold power goes down a lot. So from milliwatts or watts, I go down to microwatts. So, but then this length is small, so small that I cannot satisfy this condition. So then what is usually done is that you match the cavity FSR to the Brillouin shift, right? So this is omega p. Then you basically ensure that the cavity FSR matches the Brillouin shift. So you have to carefully design the size of the cavity, right? Because if the length is slightly off, then you will move off. But yeah, anyway, so yeah, people can also do this now in microcavities where you can reduce the threshold quite a bit. And so I posted a couple of papers on Moodle for you to take a look. Okay, so finally, one more application for SBS is slow light or like optical delays or optical buffers. We discussed this briefly for Raman scattering also, but actually with Brillouin you can get more delay because this gain bandwidth is much smaller or much narrower for the Brillouin, right? So the refractive index change is much faster, which means you can get larger group delays with SBS. So,
Sir,
yeah.
sir, I have a doubt with 3D rotation. Even with two perpendicular optical gyroscopes, we cannot detect their rotation because in other direction it will not detect it. The Doppler effect will not occur.
The other direction. What do you mean? I mean, you have like two Brillouin lasers basically, one in this plane and one in that plane.
So the rotation occurs at almost 45 degrees between the two orthogonal directions then.
I mean, you can break it into components, right? Like, I don't know, there are these Euler angles, right? For a
Yes, sir.
3D rotation, you can
3D rotation
break,
of rigid body.
break it into precession, and so that's how actual gyroscopes are also used. Sort of, you have different, even mechanical gyroscopes, you have different components in different direction, and you sort of from the different components you get an effective 3D direction.
Okay, sir.
Of course, yeah, the details are probably a little bit more complicated, right? But yeah, that's not a concern for. Right. So remember that, or recall that the Brillouin susceptibility had a real and imaginary part, right? So the imaginary part looked like a Lorentzian. So let's say my pump frequency somewhere here, so Brillouin shift down. Right, so this is a function of the Stokes frequency. So when the Brillouin shift down, you have this gain peak. So that's the imaginary part, right? And then there's a real part also, which goes like that, right? The real part of the susceptibility. And this real part of the susceptibility gives rise to a refractive index change. Right? So we consider that real part right. So then I can plot this as the change in index due to Brillouin, which is proportional to the real part of the susceptibility. Okay, so this is proportional to the real part pi 3 Brillouin times the pump index. Right, so this is something like the intensity dependent refractive index. Remember, we get terms like mod AP square AS, right? So the change in refractive index is the real part times N, so something like N2I that we had for Kerr nonlinearity. Right, so specifically I can write this index change okay. So this shape is given by this function of so this delta is a normalized detuning. So this is omega s naught, the frequency which is exactly Brillouin shifted from the pump. Right, so the imaginary part went as 1 over delta 1 over 1 plus delta square, the Lorentzian. This one goes as delta over delta 1 plus delta square. So again, it's proportional to the how much index change you get, proportional to the Brillouin gain. So the higher the gain, the higher the Brillouin coupling in the material, the more index change you get, and also it scales with pump power, the higher pump power, right? And so, right? So now you have a index which is varying with frequency, which means it also gives rise to a group index, right? Because there's a dn by d omega, and this variation is actually very sharp, right? Because this change is happening over gamma b, which is we saw is only like 10 to 100 megahertz. This change is very sharp. Okay, so if you plot the group index again, so the group index is given by this expression, as you know, right? So the change in group index due to Brillouin is the derivative of the change of this index, right? Maybe we did this similar analysis for Raman scattering also. So same thing, everything is the same, just replace the Raman by Brillouin. Right? So just the frequency scales change. Right? So this change in the group index is basically the derivative of this function, right? So the derivative of this with respect to delta ng okay, you get that expression. So if you plot delta ng, it looks like that. So this is delta NB and this is okay. So the delta NG at center at delta equal to 0 is given by this. It goes as the Brillouin gain factor times the pump power divided by Brillouin line width and effective area. Right. So basically the same expression as for Raman. We had Raman gain here and Raman line width here. But the point is for Brillouin, for example, in silica optical fibers, this GB we saw was like 2 orders of magnitude higher than Raman gain, and this gamma B is actually 2 orders of magnitude smaller than the Raman line, right? So this value can be much bigger than for the Raman case for in the Brillouin. So you can get much larger change in the index for the Brillouin. Okay, so again to give some numbers, if you take typical numbers for standard telecom fibers, so called SMF fiber, this GB is about 5 centimeter per gigawatt. A effective is 50 micron squared, right? Gamma B about 10 to the 8 per second. If I take a pump power of 1 watt, then basically for these parameters, delta NG can actually be 1.45, right? So recall that the actual refractive index of glass is about 1.45, right? And I can change, so basically I can double it by using the Brillouin again. So recall that this change in the actual refractive index, delta NB is actually very small. So that's about 10 to the minus 8. Okay, so this change in index, the actual refractive index is not changing much, right? From 1.45, it's only changing by 4 times 10 to the minus 8. But the group index, because this 10 to the minus 8 change happens in such a narrow range, that the dn by d omega is big enough. And the ng, the change in group index, can be almost 100%. Okay, which means what? Like you can delay pulses, so you can have pulses propagating at half the speed. So again, if you send pulses here, due to the Brillouin effect, you can delay them by whatever amount you want, depending on the pump power. Right? So the delay delta t, again will be this change in the group index times L by C. Right, so if I put the value of delta Ng here, you get GB pump power L K effective. And recall this GB, so P over A is I, so this is GB I L, right? Which was basically the Brillouin gain, right? So for the SBS amplifier, the gain went as e to the I GB I P L. So I can write this as the log of that unsaturated gain value. So it's going as a log of the gain divided by the line, the delay. Right? So as I increase my gain by increasing pump power, I can get more delays. Okay, so I posted a paper on Module again regarding this slow light and how basically they have experimentally shown that you can get tunable delays for optical pulses using this SBS effect. Right? It will be useful in, again, optical networks, like you have optical buffers basically to synchronize different pulses. Right, but again now, so the bandwidth of the pulse has to fit within the Brillouin gain, right? So the Brillouin gain, as we saw, is about 100 megahertz or something. So you can only get delays for, let's say, nanoseconds or sub-nanosecond pulses, right? If you go to shorter pulses, then the bandwidth becomes bigger, and it goes out of this Brillouin line. So for shorter pulses, you have to go to something which has a broader line width, like Raman. So although you can get in absolute numbers larger amounts of delay, you can also do that only for longer pulses. Then we'll launch that. Okay. Any questions on this?
But delta NB is smaller, but delta NG is greater.
Yeah, because delta NG is the derivative of this NB with respect to frequency, right? So delta NB is very small. So if you look at the absolute, the total refractive index, the phase index of the medium, that does not change much. It's 1.45. It only changes by 10 to the minus 8 or something. But if you look at the group index, around this region, right? Again, once you go away from this region, the delta NG is 0. Right? But because you have a very sharp resonance here, just around this Brillouin gain peak, you get a large value for this delta n, because this dn by d omega is large. Although the change is small, it's happening over a very small frequency range.
Okay, sir.